Good afternoon. This is Peter Esselman from the USGS Great Lakes Science Center in Ann Arbor, presenting along with Chuck Medenjen, my co-author also from the Great Lakes Science Center. I'm very pleased to have the opportunity to present the results of our 2020 survey of round goby biomass using advanced survey technologies. I consider these results close to the final draft, pending peer review and input from the Lake Committee and others. Since their introduction into Lake Michigan in the late 1990s, round goby have been a topic of keen interest of fisheries managers and fisheries scientists alike. USGS's annual bottom trawl survey has documented round goby variation in biomass since about 2006 in Lake Michigan. However, USGS's bottom trawl survey is assumed to be biased low. This is due to the fact that the trawl targets fine substrates only, which are not preferred by round goby, and also targets depths greater than 9 meters. Recent bottom trawl estimates have shown relatively low contributions of biomass to the overall fish community, ranging from 0.15 to 1.25 kilograms per hectare. If you look at the bottom right side of the slide, you can see the orange slice of the pie represents round goby's contribution to the overall community biomass. Due to their increased importance to predators such as lake trout, lake whitefish, yellow perch, and others, the Lake Michigan Committee and the Lake Huron Committee have called for improved estimates of round goby. USGS has taken this to heart and has devised and innovated a solution to sample goby over fine substrates and coarse substrates and to arrive at biomass estimates independent of the trawl survey. In the past, I've reviewed the way this method works using an autonomous underwater vehicle called GobiBot, which takes a series of photographs overlapping each other along the bottom and transects up to 15 kilometers continuously. Each image is geotagged with latitude and longitude, and the fishes within those images are labeled either by humans or by machines to establish the boundaries of the fish in each picture. This constitutes catching the fish with the camera. We've developed size estimation techniques that find the midline of each fish and estimate its total length, which we then convert to density to biomass using a length weight regression from the bottom trawl effort. And finally, we take the mean densities of biomass and numeric density and we extrapolate them to Lakewide biomass using depth and or substrate. In reality, however, the process is somewhat more complicated. This diagram shows the combination of manual and automated techniques in the data pipeline used to produce the round goby biomass assessment, starting at the upper left with AUV field acquisition, moving on to manual screening of images for usability, annotation of fish in those images that are usable, receipt of the annotated images and archiving and curation of them, a QA/QC and back and forth with the annotation company, and then automated procedures for size and density estimation, substrate characterization, and extrapolation. All of the blue boxes here were done manually in 2020, which is one of the reasons why this took so long to deliver this survey. As you'll see a little bit later on in the presentation, we're going about automating this process to the greatest extent possible to accelerate the delivery of products. In the summer of 2020, between July and September, USGS sampled 300 kilometers of AUV transects, 10 kilometers each at 30 sites. You can see those reflected in the map on the right in the pink dots. The pink dots on this map represent places where usable imagery was acquired. What I mean by usable is that we could interpret fish and habitat in those images. The blue outline here represents the 30-meter isobath, which is considered to be the deeper extent of round goby summer distributions. After all of the usability assessment, annotation, and other processing, we were able to arrive at a total number of 55,479 usable images, from which we comprised the 2020 assessment results. This represents over 10 hectares in total sampled area, and also encompassed a depth range from 0.5 meters to 46 meters sampling depth. Throughout the survey, over 42,000 individuals were sampled. Each of the individual fish detected was assigned a length and weight, from the length frequency relationship derived from the 5 years of bottom trawl data. You can see the length frequency results from all depths combined here on the left. The mean length was 46.08 millimeters, plus or minus 0.09. And you can see that it was relatively consistent in the mode at every depth, including 0 to 5, 5 to 10, 10 to 15, 15 to 20, and so on. You can see we encountered extremely low abundances at 30 and 35 meters and 35 to 40 meters. Because the GobiBot system attributes latitude and longitude to each one of the photographs, it enables geographic mapping of biomass density results, such as those shown on the left here. This is the GobiBot results from 2020 for biomass density in units of kilograms per hectare. The first thing you can notice are geographic hotspots in the northeastern part of the lake, near the rocky reefs around Traverse Bay, in the Big Bay to Knock area, and in the southwestern part of the lower basin. You can also notice relatively high biomass density numbers when compared to the 2019 bottom trawl kilogram per hectare estimate for Round Gobi in Lake Michigan. You can also see that the GobiBot survey reveals a much more spatially varied biomass density pattern that has hotspots in various locations not assessed by the bottom trawl. We found that Round Gobi biomass varies significantly with substrate. The two substrate classes that we defined in this study were fine substrates characterized by sand, in some cases with some pebbles and cobbles sparsely scattered, and coarse substrate, which is characterized by pebbles, cobbles, mixed substrate, and boulders. We found that density over coarse substrate was significantly higher in every depth bin, down to 30 meters. We also found that the mean density of biomass, after waiting for the proportions of coarse and fine substrate in the basin, was about 6.72 plus or minus 2.16 kilograms per hectare, which is an order of magnitude greater than the typical survey numbers that have been emanating from the bottom trawl survey over the past several years. Because Round Gobi biomass is so heavily linked to substrate, it makes it critical to use some notion of substrate in the Lakewide estimation of biomass density and total biomass. Again, using the coarse-fine concept described earlier, we've been working on solutions to arriving at empirical estimates of Lakewide proportions of coarse versus fine. Specifically, we've linked the substrate predictions from each of the images that we've used in our survey, which amounts to about 34,000 substrate classes, substrate predictions to coarse-fine. We've linked those to the 3-meter LiDAR bathymetry, which was made available by NOAA through the NOAA Lake Level Viewer, using data collected by the Joint Airborne LiDAR Center of Technical Excellence, which is run by the Army Corps and NOAA. The 3-meter bathymetry has visually obvious texture characteristics in areas known to be rocky reefs. Leveraging this, we defined a series of texture metrics that we applied to the 3-meter grid that essentially summarize different measures of rugosity and topography and slope in neighborhoods around each pixel. And then after linking our 34,000 AUV images to the raster grid, we were able to develop machine learning solutions that performed at close to 85% accuracy in external validation exercises. However, the LiDAR data only really covers the 0 to 20 meter zone of the lake and really mostly the 0 to 15 meter zone. And so for the purposes of round Gobi biomass estimation at the Lakewide scale, we used the empirical results to inform the first three classes, the proportional representation of fine versus coarse, in the 0 to 5, 5 to 10, and 10 to 15 depth zones. The others were assumed and degraded in coarse percentage under the assumption that coarse substrate becomes less prevalent as the water gets deeper because of the settling conditions and the lack of energetic currents interacting with the lake bed. These substrates at the lakewide scale were further used to estimate lakewide biomass density and biomass. This table is somewhat busy, but it shows how we arrived at a lakewide estimate of total biomass for round Gobi. It includes on the vertical, each depth bin in 5 meter increments, the area represented for fine and coarse based on the proportions shown in previous slide, the number of images that were available to summarize kilograms per hectare density for round Gobi in each bin, and the product of density times area yielding the biomass kiloton estimate for each of the depth bins. Adding these up shows that there is 6.57 kilotons in the fine substrate areas of Lake Michigan, and slightly less than that at 5.51 kilotons in the coarse areas of Lake Michigan. Adding these together gives us a total kiloton estimate of 12.07, which is greater than the largest biomass fraction typically occupied by bloater in recent surveys of the lake. When we compare our results to the annual bottom trawl effort, if you look to the right here, you can see that our mean biomass, this is a biomass estimate weighted for the proportional representation of biomass in each depth and substrate bin, which was estimated at 6.71 plus or minus about 2 kilograms per hectare. This estimate is much larger than the typical estimate emanating from the bottom trawl survey, especially in recent years, which have been hovering around 1 or less kilograms per hectare. In addition, we can see that the Gobi survey from GobiBot is somewhat different than the numbers arrived at by the bottom trawl. For instance, the extrapolation area considered by the bottom trawl survey includes the depth range from about 5 meters down to past 110 meters, which encompasses 3.5 million hectares, whereas the GobiBot is focusing on the 0 to 40 meter range, encompassing 1.8 million hectares. GobiBot was deployed in Grand Traverse Bay and Green Bay, unlike the bottom trawl, and so estimates were made to those locations. GobiBot's maximum depth of operation is 200 meters, but for this survey it was only deployed to 40 meters. And finally, the GobiBot sampled a much higher total number of individuals than the trawl, which typically samples between 400 and 6,500 individuals in a typical year. As with any new fisheries assessment method, there's major challenges and uncertainties that need to continue to be tightened up to yield confidence in the method. One of those that I'm very concerned about personally is the turnaround time. The second one is how well we're discriminating round gobies from sculpins and whether our survey truly reflects round goby abundance or rather does it reflect cryptic benthic fish abundance. Catch efficiency is always an important topic. When and where to sample, and finally, how do we estimate substrates greater than 40 meters or really greater than 20 meters? To address the turnaround time topic, I'll remind you that we have a high degree of manual processing taking place in the 2020 assessment that I'm presenting today. However, we've been working diligently to automate the top line of processes. You can see that in the 2021 assessment process that we are currently producing, we have automated the usability script, which saves us the need to screen 140,000 or more images. And we've also automated Gobi detection. We're currently finalizing our algorithm, but it's functioning well at greater than 85% accuracy at detecting the Gobies and putting a bounding box around them. Once that bounding box is defined, we send it for annotation, and we'll still be managing that annotation process manually. Looking forward, the 2022 assessment plan is to automate usability, Gobi detection, and to use all of the labeled images from both years of 2020 and 2021 to train the computer to efficiently discriminate the outline of the fish and automate the annotation process. This will save both money and time, and there will still have to be a manual QA/QC, but once all of these steps are automated, we have essentially a pipeline to go from field acquisition through published results in relatively brief amount of time. Round gobies and sculpins obviously have similar morphology, as you can see in the bottom left, and the truth is that our cameras cannot currently discriminate between them on a consistent basis due to resolution issues. However, we are engineering a higher resolution camera. You can see the built version of this here. It will be installed for the Gobi bot in 2022, this coming summer. However, we've seen recent evidence from Dr. Medenjan. This is a paper in review showing minimal overlap between round goby, shown here in their summer distribution, and slimy sculpin and certainly deepwater sculpin. Slimy sculpin occur in extremely low densities in the area occupied by round goby in the 0 to 40 meter zone or so. So we feel increasingly confident that we're detecting gobies in that same depth range during the summer. After finally figuring out the round goby husbandry in the Ann Arbor wet lab, we've been able to complete a controlled study of goby catch efficiency using the camera system. We're using a two-way factorial design where we're comparing day versus night and coarse versus fine sediment. We've already collected 30 replicates with 10 fish each per cross of these four class levels, and we're in the stages of counting the fish and comparing them to known abundance. We also continue to evaluate when and where are the best times to sample round gobies. Summer has its advantages logistically and because the gobies are concentrated in the shallows. For instance, in summer 2021, we conducted 250 additional kilometers of round goby survey in Lake Michigan and another 150 kilometers in Lake Huron. These results are being produced as soon as the ones I'm presenting on now are wrapped up. So we're thinking summer still has great advantages, but we're interested in understanding winter distributions as well and have a GLFT proposal under review to do just that. We've also are aware that catch efficiency can be greater at night, and so this year we'll be conducting day-night comparison. In summary, I'm proud to report that we've been able to complete the first rigorous whole lake estimate of round goby biomass, finding that there's much higher estimated biomass than previously reported. Whole lake substrate from LiDAR bathymetry has now been empiricized and quantified using a novel approach developed as part of this study. We've also had great success automating substrate detection, and we're making great progress on Gobi automated detection. On the hardware side, we've acquired a second AUV, which we'll be putting into service in summer 2022 with improved cameras. With 2021 data in hand already, we're essentially beginning to unload those now and unpack them and get to work on them. And field planning is well underway for 2022. With that, I'd like to thank you for your time and attention, and also thank the numerous funders and participants in the fieldwork, as well as our advisors and tech partners. Thanks very much.